Okay, part 3. This slideshow I'm actually kind of zip through a bit. You can read it and maybe go to your book to look at it more. I'll just sort of touch on things you kind of maybe need to know about it and how it relates to future things and what I've talked about already. So phase diagrams. So I'll show you in a minute what they are. But we have something called a triple point and a critical point. And the triple point is when solid, liquid, gas are all at equilibrium. So there is a phase where that you can have actually there is a temperature pressure that you can have all three. You can have solid, liquid, and gas. Okay, and that's called the triple point. And then critical point is temperature and pressure at which a gas no longer can be condensed. And that just means is that no matter what you do, the temperature, pressure, you can't get it into. It's gonna still be. So that'd be a really low pressure and really high temperature. And those are two way we label it. And this is just be a phase diagram, and I believe this is of water. Okay. So what you do is that you just look at, you have this for water, and then you can figure out at minus 20 degrees and at 760 torr, which is it's going to be a solid. Okay. Now if you let's say it's at that pressure and you want to turn it into a liquid, what you do is you increase the temperature. All right. This would be the triple point. Okay, and this point up here is going to be, actually it looks like it might be this point here. This point here is the critical point. So here's the triple point, here's the critical point, and F is at just room temperature. Well, I guess that's not one room temperature, but it's where the gas turns into a solid, so it's sublimation. This is a sublimation point. Okay, so this phase diagram water we just saw. The kind of interesting thing here is how it slopes this way. So by increasing pressure, so if you increase the pressure on a solid, you can turn it into a liquid for water. And the reason why that is, so for ice, so if you take ice and you add pressure to it, okay, that pressure is going to do, it's going to break apart the interactions of the ice, and it's going to make it liquid. So it's going to be like a super cool liquid. And that's how like if we go on how glaciers move. Glaciers are giant pieces of ice that are sitting on land, and there's so much pressure on the bottom of it that it's breaking apart the hydrogen bonds, but the temperature is still below freezing. Okay, and when it's below freezing, and pressure, but it still can form a liquid. So you can have high pressure that forms a liquid, and then that's on that liquid it can slide. So that's why glaciers move. And also, like if you go ice skating is that when you press down on your blade causes presses against the ice, which causes the hydrogen bonds to break. Temperature's the same, so temperature stays the same, but you increase pressure. So temperature stays the same, increased pressure turns into a liquid. Okay, so if you keep temperature same, increase pressure, the water they turn it, and it's because it breaks the hydrogen bonds. Okay, so this is carbon dioxide. Carbon dioxide is different. It has different. You can figure out all the points, but again, let's take a look at this ratio. As you increase the pressure at a given temperature, you're more likely to turn it into a solid. Okay, and that's because you're pushing the. So nonpolar molecules, you by increasing pressure, you increase the interactions, and therefore more likely to cause attractions. Okay, because one of the things that increase it, so nonpolar molecules are increased by being closer together. All right. So, but for polar substances, if you push them too close together, you sort of mess up their array. So water molecules are naturally aligned. Okay. If you shove them together, they're no longer aligned perfectly. For carbon dioxide molecules, when you shove them together, they don't have to be all aligned in particular, and so they just cram all together. So if you increase pressure for nonpolar substances, you will you're more likely to turn it into a solid. All right, supercritical fluids. Go just read that. Le Chatelier's principle. We talked about that a little bit, and we'll get a lot more into it, and over the next few weeks. So let's just read it, and if there's a question on the test, you can use your notes here. Like I said, anytime you have if you're at constant temperature and you don't let substance leave and you have closed system, if you have a liquid and a vapor and they're at constant temperature, this should be constant temperature and pressure. Okay, there'll be an equilibrium that will keep the liquid to vapor ratio equal by exchanging the number of particles equally. All right, so there might be 80 of these and 400 of these. All right, so at equilibrium, you might have 4 going this way and then 4 going back this way. So if you did increase temperature, you would force the reaction to go to the right, and we'll talk about that because no longer. So heat is also part of the equilibrium here. Is that as a vapor turns back into, so there's a certain amount of heat ratio as well. So the ratio of heat to vapors is going to be constant as well. So if you add more heat, that means the reaction is going to move to the right to try to keep the heat the same, keep the ratio of the heat to vapor the same. So that's the thing you keep remember. So if you add liquid, okay, so if you add more liquid at a constant temperature and pressure, and it's already at equilibrium, that means is that so let's say now you have, instead of 80 to 400, now you have 100 to 400. What's going to happen is some of the liquids is going to turn into vapor to try to get that ratio again the same as 80 to 400. So the 100 will go down and the 400 will go up. Now the opposite would be true. I mean, then you could do this. You could add heat, and if you add heat, the ratio of heat to vapors, and therefore heat will have to come. They'll have to come to equilibrium and should move to the right. Okay. No, so we're going to be doing a whole lot of these. Okay, we can do the other thing. As long as you're at equilibrium, let's say you take away liquid. Okay, so now that means you have less liquid. So, but the ratio still got to be 480. So now you only have 60. So that means some of the vapors got to turn into liquid to get that ratio the same. And we say the equilibrium shifts to get the system back into its equilibrium, because the equilibrium has to equal this 400 over 80 or 5 to 1. Okay. If you add more vapor, the ratio won't be 5 to 1, and it'll go to the right to get it back to the left to get it to 5 to 1. And again, we'll be using these a lot. All right. There, it's liquid. Now, I don't know if there will be any problems with this, but we can, there's a equation called Clapeyron, and we may, if we were in class, I may try to derive it for you. But it just says, it starts out as this, and then what we can do is, if we're given where P is some pressure, P1 and P2 are two pressures and two temperatures. So let's say I can figure out, if I want to find out P1, and I know P2, T1, and T2, I can and the heat of evaporation, I can figure out C cell for P1. And here's a calculation to figure that out. I just let you go through it. Okay, just plug the numbers in, and units cancel out. All right. Now, so what we get is the ratio here, and then what you can do is solve for P2. Okay, your turn. Okay, go ahead. And you can figure it out on your own. Now, I don't know if any of these will be on the test or not. Okay, here's the solution. Just plug everything in units, work out. Just remember here is that this says joules, and we end up with joules per mole, and you can change it to kilojoules per mole. And actually, we have to be careful about should be a plus in front of here. Okay, it's because you have to give the direction. This tells me that this is endothermic reaction. Sometimes this should be a negative value. Types of solids, you can have crystals. We have highly regular arrangement of components, amorphous, or it's not regular. Okay, they form lattices, we say, so it's a network. Okay, symmetrical, three-dimensional, and we'll go over these. Now they can be atoms or molecules, ions, and so forth. Are the packing components. Okay, and they can be in different arrangements. These lattices, and they're three-dimensional. That's why we call them a lattice. So, and then what we have is the lattice is made out of unit cells. So, and actually, the unit cell is the center point of each particle. So that's why this thing kind of looks odd here. So these are center points. So it's the smallest repeating unit. All right. And we'll see these as we go around. There are three types of 3D units. Simple cubic, and it looks like this. We have an atom in each corner. The edge length A is equal to 2r, where r is the radius of the atom or the ion. Then you have something called body-centered cubic, where you have a particle in the middle of the cube. Okay, the edge length is 4r over the square root of 3. And then you have face-centered. Now it's hard to see here, but you have your 4, and then in the center of that face is a particle. All right. So, and then if you look over here, this has over here. So you have your simple, body centered, and cubic. if you get into material sciences, you'll go over this a lot more. Okay, edge and length, you see if it has its own formulas. Okay. All right. The close packing. You always want to have, usually things want to be close packed, but doesn't necessarily have to be. Depends on how the attractions are of the molecules and atoms, ions, so forth. The best packing is 6, okay? So take this guy here, you'll notice that it has 6 neighbors. And that's just natural, all right? That's how spheres pack. And then they can pack in this direction as well. And then you can have a third. Okay, 3D cubic lattice. Okay, so here's your simple cube, and then these can pack into to a three-dimensional simple cubic lattice. So the unit cell is cubic, basic cube. Others, so you can, other kinds of cubic lattices, you can have this. Okay, face centered. Okay, here's your body centered. All right. So this is your face, and these are your body, and they can form a lattice as well. In terms of okay, again, if you have an ionic compound, it will form a crystal, and the crystal can be one of these, usually one of these 3 shapes. It turns out they could be more than these 3 shapes, but so common ion might be sodium chloride, and where so you look at this, it's kind of big, but what you get is that you will have each big one is a chloride, and the small one are the sodium. And you'll notice this is face centered. And if you look at each chlorine is going to have 6 sodiums attached to it. So you're going to have 1, 2, 3, 4, and there will be another one here that's attached to this side, and then the other side in the middle there will be another guy over here. So each sodium has 6 attached by an ionic bond. Okay, and here's some other examples of common ionic solids. Okay. Now, so like the chemical formula for this guy is CS. So this is the chemical formula for this, CS plus Cl minus. But if you look at the structure, it looks like there's only 1 Cl for every 4 CS's. Okay, and then you go, oh, that looks like it's CS4 Cl. Well, it turns out that each of the CS's has will also have, so when you look at the overall structure, there'll be the same amount of cesiums as there is chloride. But in one unit cell, the ratio doesn't look like. That's a zinc sulfide is another example. The chemical formula is ZnS, but the ratio looks like there's 1, 2, 3, 4 zincs and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 sulfurs. But when you put all of these guys, when you put many of these cells together, the ratio will always be 1:1. And calcium chloride is Ca. Chemical formula is CaF2. Okay, but when you count up all the particles inside the unit cell, it's not CaF2, but if you count up all the particles that are in the whole lattice, there will be 2 fluorines for every 1 calcium. Okay. And this goes into the more intricacies of what the cell looks like. And we're not going to get into this. I just want to show you that it exists. And again, if you have problems like this on a test, you can use this video to help you out, figure out your answer or your book. And again, if you take material science, you'll be definitely spending more time or electronics time going over this. Yep, and when I was taking my class in material science, I had to do all kinds of these calculations, and I don't want you to drown you out with this. But here it is. You can take a look at it and see how it works. Okay, so go ahead and try this. And then you can see that you get the proper ratios when you do that. All right. Some factors affecting crystalline structure, size of atoms, and the ions involved, stoichiometry, that's like how many atoms are per other atoms, the materials involved. Now, amorphous solids, then these guys that don't regularly form very good crystals, maybe like glass. Okay, it's more of like threads. Again, remember if I told you that glass actually kind of behaves like liquid. Xray crystallography is a way of measuring what kind of crystals they are, what kind of crystals you have, and also the shapes of the crystals. And so X-ray crystallography is a way of taking pictures of crystals. And it has to do with the X-rays have about the same wavelength as the distance between the atoms inside a crystal, and therefore they actually a little bit smaller, and then they can actually take pictures. When you take a picture of something, the wavelength that you're taking the wavelength that you're using to take the picture has to be smaller than the substance you're taking a picture of. So you're taking a picture of a wall. Light has small enough wavelengths to not pass through the wall. And if you get into this, and this is more physical chemistry, I'll explain it. And this is how they actually, X-ray crystallography is how they come up with structure of DNA. When the original structure of DNA, what they did was they made it a crystal, and they used X-rays as the light source, and then the X-rays actually use X-rays as a way of taking pictures of the crystals of the DNA. And that's how they take pictures of proteins and other really small objects. Okay, and this shows you how that works, and it's pretty cool. I don't know if you see the original picture of DNA, it'll look something like this, and you go, that looks nothing like DNA. You know, DNA has that structure like that. But what they do is they take this picture from the X-ray, and what they do is they take a a mathematical computation called Fourier transform. Fourier transformation. And when they do that, that calculation will turn it into something that looks like something we can recognize. Okay. And if you, they may cover this in physics when you take physics. I believe physics too. I don't want to go into it a whole lot. Just yeah. And my guess is that you can just scan through it. If you got a problem with the problem, you can. Here's the equation, Bragg's formula. You can use that, and you can just solve. Okay. Given all the information. X-ray diffraction measurement revealed that copper crystallizes with a face-centered cube, in which the unit cell is 362. PM stands for picometer. What is the radius of the copper atom expressed in picometers? Okay, so here's what you have. This is basically a geometry problem. You have the sides, a squared b, and so forth. You got to find the diagonal. A and B are same, so they have to equal C. So you get that, and so then plug it because you know it's a what kind of cube, what kind of cell it is. Use that formula, and then you get your answer. Okay, and I'm just, if you want to go ahead and do these on your own, but again, I'm not gonna. Okay, ionic crystals, this is more important here. Have cations and anions. Cations positive, anions negative. They're relatively hard, and that's because of the strong interactions. They have high melting points, again, because they're strong interactions. They're brittle because they form crystals. They have strong attractions between the ions, electrostatic. They do not conduct electricity in a solid state, and that's because the negative ions equal the positive ions. But when you separate the ions, they can conduct electricity because the positives and the negatives are no longer balance each other out. Okay, so do this problem here. The next slide will tell you how to do it. So we want to determine the unit length. We know it's face-centered, so it'll have its own formula. The atomic radius is terbium is 175 picometers, and then we want to find the cell length. It's 495. So the diagonal of the cube is 4r. And it's using the face-centered, and the diagonal cube is square root of a times square root of 2 times a, and then you just plug things and you get your answer. Okay, besides ionic crystals, you have covalents, and those can be like glass and rocks, and so there's like silicon dioxide that makes up sand and so forth. In rocks, is that you have the atoms are going to be covalently bonded together instead of ionically. So okay, they tend to be very hard. That's because they're covalent crystals. Like a rock is very hard, and covalents are stronger than ionics, so they tend to be harder to break apart. Very high melting point, again, because of the crystals are held together by covalent bonds. Examples, like a diamond, right? So a diamond, all these guys are carbons, and all the carbons are connected by a covalent bond. So this guy would form it forms a crystal, in a crystal, and it'll have a very specific shape and structure, and it's very hard to break because these are very strong covalent bonds. Silicon dioxide, like sand, same thing. And quartz, silicon carbide. All right, and then you can have metallic crystals, and that's like just metals. If you have a metal, it's actually a crystal. And the way to kind of think about metallic crystals is that we say that the electrons are kind of a sea of electrons, and so the positive ions or the nucleuses of the metals tend to stay put. But what happens is the electrons can easily move around inside the structure, okay? And that's one reason why metals are good at conducting electricity, is because these electrons can move around in this cloud. So electrons can move around in the lattice. Okay, metal crystals conduct heat or electricity, and that's because the electrons can move around. And they shine, and that has to do with the electrons moving around as well. The electrons vibrate easily, and when they vibrate, they give off light. That's pretty cool. So the moving around electrons. Okay, so I just kind of zipped through that one, and just give you some background. There may be some questions on the quiz. There'll be questions about quiz on the quizzes that do with these, and if there's calculations, you can go ahead and use the slides. In fact, all these PowerPoints you can use for any of the at least this test. You can use for your quizzes and tests, and so you'll be given enough time to do that. So I'll have all three of these out, and I'll have the quizzes associated with them over in the next by the end of the week. Okay, so we're done with part 1, and then next thing we'll do is we'll actually apply this to big chemistry. That means how do we use it in everyday chemistry. All right.